Okay, welcome everybody for this next edition of the 25 years of IPN Colloquium to celebrate the achievements of what we did within IPN, but also give you a good overview of what is happening in computer science nowadays. And I'm very pleased to announce today's speaker, Andreas Zeller. Andreas is working at the CISPA Helmholtz Center for Information Security and a professor for software engineering at Saarland University, where he works on automated debugging, mining software archive, specification mining, and security testing. Uh, he's received several awards. He's an ACM Fellow, also holds an ACM 6 of the Outstanding Research Awards, has received two ERC advanced grants. Most recent one is called Semantics of Software Systems. This is all in the official bio. I also looked around a bit more, and I also found that so he's an active proponent of open science, and he was the one that helped introducing systematic artifact evaluation at FSE in 2011 already. And then I found an interview with you where people were saying that you were an active communicator and love to talk about science in an accessible way. So I'm very much looking forward to your presentation. So Andreas, the floor is yours.
Yeah, thank you very much, Marika, and thank you, Sana, for having me here today in this very prestigious event. And also a warm welcome to everybody here in that meeting. I very much appreciate you being here. I understand that the Christmas time is a time of fun and a time, but also a time of stress. So I'm very happy to have you all here today. I hope you can hear me all right and you can see my slides. If not, drop me a note, I guess, but we've tried things before. Things should work well. Okay. So today's topic is should AI coders experiment more? And the idea of this talk is to get you an idea of what future AI coders or AI coding agents could be doing if only they would experiment more. So this whole thing starts with the current worry of the day. Will AI-generated coders replace developers? So this was just recently on Business Insider. At Anthropic, 90% of the code written by the teams at the company is done by AI. He's not replacing engineers just yet. And I wonder, why is that just yet in here? Last year, we had a Suffolk expert who says that AI will replace human coders in 10 years. And the same thing also was on Medium. ChatGPT will replace programmers within 10 years, predicting the end of man-made software. Is this really going to be the case? Well, here's an overview, a survey of developers using AI techniques this year. 82% of developers use AI tools weekly, so AI has made it into the mainstream. 25% of all the new Google code is produced with assistance from AI, and developers save time about 30 to 60% on coding, testing, and documentation. On the other side, developers are also slightly worried. Code duplication is up tremendously because AI keeps on suggesting the same code over and over again, rather than, say, us coming up with appropriate abstractions for that. 75% of developers review every AI snippet. That can be seen as good news, but it can also be seen as bad news, because this means that 25% of developers just let AI-generated code through without ever reviewing it. And not very surprising, 62% of developers are worried about the potential technical debt, meaning that the code becomes harder and harder to maintain and creates a burden on future, on whom actually? On future AI systems or on future developers? That's something we do not know. So what is AI being used for at this point? It's mostly being used for code completion. So pressing tab, 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 and you get whatever might fit best into your current code. Basic testing and documentation, meaning that we're generating simple unit tests, configuration files and setup scripts. That's also on the easy side, and simple functions and utility logic. And one common pattern across these four AI things is actually All of them are rather simplistic, I should say. But well, there's plenty of simple tasks in development, and maybe, just maybe, we can advance the whole thing towards more complex tasks. So what's the future of AI in development going to be? That's a very, very good question. So if we project things in time and if we project the capabilities of AI, while today we might still be at the stage of rather simplistic functions, actually, even a simple hello world function can become super complex if there is a printf involved and if you really want to analyze what printf is doing, but keep that apart. The assumption is that today we're still at an early stage, and in the future we'll be able to produce, we'll have AI that produces immensely complex and immensely big software stacks. I brought an example. This is from 1968. This is Margaret Hamilton, chief software engineer at NASA, showing off the source code of the Apollo 11 mission. So that's quite a pile of software when you print it out. And actually, still today, well, if you look at the software, whatever that's driving an Airbus, for instance, well, a single pile like that is not going to suffice. You will need a container of paper for that. But to give you an idea, this is the stack that brought people to the moon and back, and every line in there is precious. And every line in there is important for getting the mission done. And that's still a sharp contrast to what AI can do today. So while today we are in a situation where AI can do small coding tasks, being able to maintain and to evolve an existing system, which actually makes up half of the task of a software engineer, that is still an open problem. And it's mostly an open problem because complexity of software stands in the way. If, again, we make a graph here, we look at the number of lines of code in a piece of software, and then we look at the complexity of any task that involves the entire code, well, unfortunately, this complexity also grows exponentially. So even if you have an AI whose capabilities grow exponentially, well, you're going to need that because all of these tasks on code also are going to grow in an exponential fashion. Why is it? Why is that so? Why is software complex? Why is it much, much harder to maintain software than, say, to build new little pieces of code? Well, the simple reason is that the software is composed of hundreds, thousands, 10,000s of individual modules. Call them functions, call them units, call them whatever you like. And all these individual units are connected to each other and interplay with each other, meaning that any change you may make to one particular part in here, well, whatever, pick any module in here, is going to affect the other modules and thereby also affect the stability of the entire system. This complexity and this interconnection of things also is a big problem in AI. Of course, today AI is absolutely great in generating pictures that are all beautiful, such as this one. It's hard to spot any mistake in today's AI-generated images. However, if you wanted to tell an entire story made of multiple images with continuity between these images, you will soon realize that this is one of the biggest challenges that AI is still currently facing. We can generate individual images, so far so good, but generating a consistency between multiple parts as we have them in big pieces of software, consistency between these parts, that's very, very, very hard. In other way, in other ways, we can have AI generate an individual picture so far. Yeah, that's great. But maintaining the consistency between all these parts such that they play well together. And in a movie, we'd say, okay, there has to be continuity between the individual scenes. In pieces of software, it doesn't suffice that the whole thing compiles. The whole thing must run and it must do the right thing. And because we are sending people to the moon. This is a big problem. And this problem, of course, is known in software development for decades. This is the problem of context, as we name it. And it's a problem that is sometimes conveniently ignored. For instance, when we're talking about software verification, 30 years ago, the idea was that we can easily prove correctness of individual modules. And I have to say, this is pretty much routine work today. We can do that for individual modules. That's great. But getting things to scale, getting things to work and be correct at the scale of mission critical software, that is still an immense challenge also in software development. What we're currently doing is we are conveniently abstracting away all the other modules and we're assuming they just work fine. And then we can prove correctness of individual modules and we can reason about individual modules. But, well, we cannot take holistically the whole thing into account because this is rapidly overwhelming all kinds of reasoning systems that we do have. And there's no reason that this problem of context would not also occur in the same fashion in AI systems. Of course, well, yeah, well, we may be able to feed more and more into our context windows in AIs, and we will make our LLMs even more bigger and even more. But even then, what I brought along here, yeah, this is just for the fun. I brought along some piece of code. This is part of the Apollo 11. This is part of the Apollo 11 source code. So this is the file called burn baby burn, the master ignition routine that apparently turns on the ignition of the lunar module. Okay, so this is almost 50 years old. Fun fact here. And yeah, it turns these are the first 5 lines here. This is all assembler. Uh, we have a bank 36, set lock P40S bank, eBank equals which count star dollar dollar slash P40. I have no idea whatsoever this means. Maybe we can look up somewhere what a bank 36 is. Maybe we can look up somewhere what count star dollar dollar means. Maybe we have some documentation about this assembly routine, but how are you going to figure out what this code does without, well, actually, how are you ever going to find that out? This goes on like there's even comments in here. Noli se tangere, don't even touch this. This is Latin. Don't touch me. Don't touch this because this is also critical. There may be some comments in there. TCF full G not TCF. Well, what does this stuff do? We have no idea, and we cannot find it out simply by looking at the source code. Without knowing the context of the lunar lander module, without knowing the construction, without knowing what this hardware is, there is no chance we can find out things simply by learning from code. And of course, maybe, just maybe, we have a chance that AI is going to develop all these capabilities by itself. We'll have AI generating more AI, and then we'll all end up in the singularity. But actually, there's doubts on that. There's doubts that this curve is going to go like this. Actually, the fear is more that this curve is going to be logarithmic in terms of capabilities, because there's a limit. There's a limit to what AI can learn, and this limit is the limit of available data. There's only so much you can learn if the data is not available for you. And this is a problem that actually is not posed by me. This was discovered by or posed by two very important AI researchers recently in a position paper, Welcome to the Era of Experience, written by two folks. One is David Silver, the other one is Richard Sutton. And if you don't know them, David Silver is the inventor of AlphaGo, or the main person behind it, got the ACM prize in computing 6 years ago. And Richard Sutton was the PhD advisor of David Silver and actually got the Turing Award this year. So if these two have something to say, well, I guess we should listen to them. And they are putting forward two important points here at the beginning of the paper already. Read the entire paper. It's a super exciting read, but let me just guide you into this paper. Okay, so what they're saying is that what they're posing is that the majority of high quality data sources, those that can be used to improve an AI, have either already been or soon will be consumed. And valuable insights, such as new theorems, technologies, or scientific breakthroughs, cannot be captured by existing human data. Okay, everybody, now go out and sell your AI stock. The AI crash is imminent. Now, that's actually not what they do. They say we need to come up with a new source of data, that allows agents to learn continually from their own experience. That is data that is generated by the agent interacting with its environment. And this is the plan here, in which we're going towards an era in which experience will become the dominant medium of improvement and ultimately dwarf the scale of human data used in today's systems. So what is the era of experience going to be about? Are we going to have humanoid robots dancing in the streets and figuring out what happens if you cross a red light without looking left and right, or opening your cupboards and finding out that, well, your plates actually break if you let them fall? I mean, toddlers are actually super great in learning from experience. And since we all have been toddlers, we learn a lot from experience. So why not? Okay. But but that's just one way of putting up this experience. You know, when we have software, we can experiment with it like crazy. We can put the software in a sandbox, and then we can experiment with it without having to fear any interaction, any repercussions in the real world. We can reset the sandbox at any point, and then we can try out what works. This is actually also the same thing that the NASA engineers did it. They ran plenty of simulators on their software. And then you can see, okay, I'm sending in an input to my software and I'm getting some output out of that. And now, since the entire piece of software is involved, and since there is no abstraction whatsoever required, we can do the thing on the real software. All we need is an environment that the software interacts with. Then the problem of context, as we had it before, the problem of context simply goes away. And if you compare the amount of data that we can learn, or that an AI system can learn, from observing only code. Okay, this is a nice faucet. You can turn it on. There's water coming out. So far, so good. But compare that to the amount of data that you can learn from experimenting with code. You can run the code under all possible circumstances. You can figure out what it does here. What does it do? What does this button do? How does this affect the output in any way? And we need not even be limited to the externally visible features. We can also think about if I press that button, what value is this variable going to take? Will this button actually ever affect this variable value? Is this function going to be called? Is this function not to be called? Will function A call function B? All this is data that we can observe from executions. And this is indeed such a vast amount of data that I think that very few people actually so far have actually attempted to mine that data and to make good usage of it. And definitely not at the scale of Apollo 11 software. So, but when we want to experiment with software, we have three challenges. The first challenge is, where do we get the inputs from? That's a challenge. How can we process the outputs? And that's also a challenge. And finally, how can we train an AI with that? Yep. Three big challenges. And fortunately, the first two challenges have long been addressed in software engineering, notably in software testing, because getting inputs, processing outputs, checking outputs, well, that is the essence of testing. And third, I'm also happy to report that that indeed it is possible to train an AI with that. Okay, first things first, testing. In order to systematically test a system, one of the easiest way is to specify the input of the system. I'll stick to simple strings here. Strings can encode anything. And in order to specify what inputs look like, a typical way is to use formal grammars, which actually happen to be the oldest technique for systematically testing systems, going back to 1968. Hey, that's the that's the year of that's the year when the photo of Margaret Hamilton was taken. Ha, everything important happened in 1968. I was born not in 68, so sorry about that. Okay, good. Grammars. What is a grammar? For those of you who have never seen grammars before, well, a grammar is a specification of a language, and here a language is a set of inputs. Grammars can also be used for natural language, and then you can specify whatever the syntax of English, for instance. Not much fun, but yes, you can definitely do that. And here we have and the grammar is composed of a number of expansion rules. And in each rule, as you do have non-terminals, these come in these nice little angle brackets. These are placeholders for what eventually becomes a terminal symbol. Non-terminals come in these angle brackets. Terminals do not come in angle brackets. What can we do with a grammar? Most notably, we can feed it into a test generator, also known as a fuzzer. If you talk to security people, they call it fuzzers. You talk to software engineers, they call it test generators. You talk to people in formal methods, they call it producers, but it's always the same thing. How does this work? A grammar as a producer works as follows. You start with a symbol out of your grammar that is the start symbol, conveniently named start. And then you go and you continue, you have this term here in the middle of things. Here we have it. And then you go and you continuously replace all the non-terminals in that string with other replacements that can be found on the right-hand side in your grammar rules. Here we do have start equals expression, and therefore a start symbol gets replaced by an expression symbol. Here we go. Start becomes expression. That was easy. Now we continue this thing. So for expression, we also look up one of the rules. And here we do have multiple alternatives. For instance, we can replace expression by term minus expression. In a producer, these alternatives are typically selected randomly. So in our case, expression becomes term minus expression. So now we have term minus expression. Now we need to replace term. And term in our grammar becomes factor. And now a factor becomes int.int. In the next step, the first int becomes a digit. The second int also becomes a digit. And the first digit becomes a non-terminal, namely 8. And the second digit becomes 2. So if you haven't noticed so far, the grammar actually produces arithmetic expressions. And if for the second expression we increase the length of things somewhat, then we can get an arithmetic expression such as this one. This was nicely produced by the grammar above. And here you see that this can create very complex inputs. And we can also have the grammar systematically cover all alternatives. So all digits are covered, all operators are covered, um, all ints and floats and all digits in floats and all combinations of things can also be covered. That's all part of the art of creating inputs. But I can tell you that if you take this expression and you feed it into a calculator of your choice, this will happily execute every single bit in the calculator, every single bit in the calculator there is. So what do we do with that? So bit of self-advertisement here. We have built a tool called Fandango, which takes such grammars and actually is a super efficient and super powerful producer for such inputs, or test generator again. So the tool is named Fandango, Fandango for the Spanish dance. And here we can specify inputs as grammars, so far so good, but we can also use Python constraints on top. So we can express things such as whatever the sum, every sum should be at most 100, or we can say the length of the input should be at least 1000 characters, or we can have checksums and other stuff. I'm not going to talk much more about that. The important thing is that it's expressive, it's modular, it's fast. And with a grammar like this, Fandango can easily create hundreds of thousands of inputs per second. So and all these inputs would be also diverse. So there's absolutely no shortage of synthetic input data in here. So what do we do with that? Well, normally we use it to test programs. That is, we produce inputs and we can also use the grammars to parse and check output. So we have an input specification, say a Fandango file, a grammar. We feed this into Fandango. And then with Fandango, we create inputs to a program in question. And then the program produces outputs again, and we can parse them again with from an output specification. And then we can check whether the program does the right thing. This is standard software testing. Where do these specifications come from? Well, this is another line of work in our research. We extract such grammars from existing documentation. We have Kwang here from Volkswagen. Hi, Kwang. Happy to see you. Happy to see you here. This is Kwang's work, and we also have Leon Betscheider here in the audience, who's working on extracting such grammars from existing programs. So if you're lucky, you don't have to spend days and days writing these grammars because you can already extract them from existing sources. So the main problems of how to get inputs and the problems of how to process outputs are already there. By the way, both inputs and outputs here are structured so we can access their individual constituents, also meaning that we can also that we can tokenize them, and we can also access all their other features, which becomes important in the next step. Because while we are doing lots and lots of work in testing, one of my pet applications of this is actually to use these input-output pairs to train models from that. And here we are. This is the connection to AI. We have a nice tool called Modelizer that takes these input-output pairs from the program and synthesizes a transformer model from that. This is a vanilla sequence-to-sequence neural machine translation model. You probably all know the paper "Attention is all you need." Yes, this is exactly the kind of model that we produce from here. So all these inputs and outputs go into the transformer model, and then, oh, by the way, there's a paper on that, of course, too. Learning program behavior models from synthesized input-output pairs. And once we have trained such a model, which actually is very fast and efficient, no comparison with whatever training an LLM, we're talking about training such models in the space of, well, on my laptop, something like 2 hours or so on a decent program. Then we get a model that happily takes inputs and also produces outputs, and it actually simulates the exact same thing as the original. So, for instance, if we do have a pandoc converter, pandoc is a tool that converts various input formats into various output formats. And the pandoc converter takes, say, markdown inputs and converts them into HTML. Then we can learn a model using Modelizer from that, using a synthesized input-output pairs. And then the pandoc model will happily take the same inputs and produce the same outputs. In the case of pandoc model, we have an accuracy of more than 99% with that. So the question is, of course, why should I want to do that? I mean, I have the original pandoc converter. Why do I need a model for that? Well, there's multiple reasons for that. First reason is that the model by construction will be differentiable, meaning that maybe I'm interested only in part of the output, so I don't need to run the entire I don't want to run the entire converter if I'm only interested in a particular property. So this is one thing. Second, maybe I don't trust my pandoc converter, and of course the pandoc model will be free from malware or any hidden behavior that may be lenient somewhere in the pandoc converter. The third reason, however, is possibly the most interesting, because I need not only train the model from input-output pairs, I can also train it from output-input pairs. And then the pandoc model actually reverses what the pandoc converter is doing, meaning that I can feed in in this case, I can feed in the HTML, and what I get out of this is then again going to be markdown, and is going to be semantically equivalent markdown. In this case, you'll find that there's small differences in here. So in the uppercase, we trained from something with 2 underscores, and now we get 2 stars in here. But in markdown, both of these actually mean the same thing. This is a strong emphasis, and both of them translate into the same HTML. And so this is also something that we get with in our experiments, that we get with a precision of 96% and more. However, the nice thing is we can always check whether we're doing the right thing, because we can do a bit of reinforcement learning in here. And what we can do is, for instance, after creating the suggested input, we can feed this again into our original program, the pandoc converter. And then we can check whether the output of the pandoc converter is actually what we fed into our model in the first place. And if there are any differences, well, then we can feed them back into the model and tell the model, well, you did a mistake here. Please please go and refine, and we can do this in multiple loops. And with such refinements, well, the the effect is that either at the end you get either in the end you get a correct result, or Panda model is simply going to say, no, I won't be able to do that. And in our results, we get, as I said, great accuracy. So for instance, for the forward and backward direction of pandoc, markdown, HTML, 99.39 and 99.55%. This is almost perfection. SQL to KQL, we're also in the 96 to 99% range, but there's also limits to things we can do. So, for instance, for pi expression to LaTeX, we're only at 88%, but this still means that in 88% of all cases, well, you get a correct result, and the other 12% that does not, where the verification steps do not work, then you're simply not going to get a result. That's it. The important thing here is that the outputs, again, of the program can be arbitrary features of the execution. So it can also be a stack trace. Dear transformer model, please produce me an input that generates this very specific stack trace. So when your program crashes on your system, for instance, typically a stack trace is being sent off to Microsoft or to Apple or to Google in order to help them debug the whole thing. Well, with the transformer model, people can immediately synthesize what the input that will have produced this stack trace is. Same goes for variable values, same goes for cordams, that is the final state of a program. You can ask the transformer model for an input that results in this very situation. And this opens up plenty of applications, because you can actually see the transformer model as an expert on your program that can explain why is the state of my program as it is, why is the output of my program as it is, and it can then tell you by supplying an appropriate input. So this is not the only way to train an AI, but this is clearly a way, and a successful way, to train an AI from plenty and plenty of experiments, well, where we have arbitrary amounts of data to train from and to learn from. So again, welcome to the era of experience. So how about code? So far, we only talked about input and output. And another line of research in my group, we use generators to generate code changes, synthetic mutations to the program code. So we are replacing a call by another, we are replacing an operator by another, we are replacing a configuration setting with another one, just random changes. And then we check, how do these changes affect the output? And again, we process these, we feed these into an AI system. In this case, we use an LLM for that purpose, so we don't train things from scratch, because here we need to reason about code. This works better if you do have a foundation model. And then if you have such a fine-tuned LLM, then you can say, okay, dear LLM, I would like the output to change in a particular way. What do you know about that? And being trained from this combination of code changes and output changes, the LLM will then happily again predict the code changes that are required. Since before, in the experimentation phase, the LLM, the AI system, has learned which parts of code are responsible for which parts of the output to be produced, and it has learned which changes can be made to result in which changes in the output. And if you reverse the whole thing, yes, then it can predict which code needs to be changed. And again, this is a paper we had also this year. This is Laura Plein at the FSE student research competition, predicting software changes from desired behavior changes. And the title says it all. You want the program to do something differently. What can we do? And it predicts the change that is going to be needed from that. And again, I pose that such changes can only be suggested if you do have trained the system on sufficiently many examples such that the AI knows from experience what needs to be done. So again, welcome to the era of experience. Here's a nice little graph that comes from this very paper. So in which, again, over time, the attention on reinforcement learning first started. So with Atari, AlphaGo, AlphaZero, systems that learned from experience to become better, became better and better again. This was the era of simulation. And then, well, now we have ChatGPT, which actually works from human data, but definitely not from simulation. So now there may not be sufficient attention to experience, but the authors pose that this is going to change tremendously, notably when when AI systems start how to learn computers, and this is when we will finally reach the era of superhuman intelligence. I am not sure whether we can get to superhuman intelligence in general. That's for someone else to discuss. But as it comes to coding, we may come close. So let me give you an idea of what your future program-specific expert trained on your program with millions and millions of experiments on how code changes affect the behavior and how input changes affect the behavior. Okay, here's trained. Your future program-specific expert has done everything, has seen everything, and therefore can predict the effect of input or some code change, can tell what needs to be changed, can tell what needs to be input in order to achieve a particular effect, and keeps on experimenting and learning all day and all night. So, and of course, this need not be a single expert on a single program. You can also imagine that there would be multiple experts trained on multiple programs that all coordinate with each other to learn even more. Now, what would an interaction with such an expert look like? Let's say we're again in the Apollo domain, now Apollo 13. There's been an explosion. What could this be? Oh, yeah, my data shows this happened right after steering the oxygen tank, because your expert, of course, can also track the data during while the program is executing. And well, actually, you should have predicted that it was an explosion, but let's assume this is hardware. Okay, actually, it was hardware in Apollo 13, so this is out of the domain. Can you change the configuration to minimize energy consumption while keeping oxygen levels up? Apollo 13, so those of you who've seen the movie or read the Wikipedia entry know that finding out such a configuration actually took days and days with all the hundreds of NASA experts. Of course, your program-specific experts will already know that there is a configuration that will do that. And can we change the flight software to get back to Earth as soon as possible? Of course, great idea, Andreas, like ChatGPT. I'd propose the following code changes, all tested already. Again, our expert knows, our expert has done already, has anticipated things already. And the same also goes for what is the best order to turn the components back on. Yes, the interaction with your expert will be feeling like I am talking to some demigod-like entity like L 9000 in 2001, A Space Odyssey, a system that knows more than you, a system that has way more experienced than you, and a system that will have to do its very best not to always demonstrate its superiority to you. What are the challenges that lie ahead of us? Well, so far, 50% of software development is coding. That is something that we can continue to address using the standard LLM methods. But now we're talking about maintenance, how to maintain existing code, how to embed your code into existing system, and how to make your code work at a large scale. So first challenge is the cost of training. If you want to run thousands to millions of automated experiments, this will be expensive. This will be expensive in CPU power because you need obviously thousands to millions of runs, and this will be even more expensive in terms of model training. You're going to need quite a number of GPUs for that. But when I say the cost might be the same to training a human, if you're bringing in a new, even senior developer, and ask that senior developer, hey, here's this piece of software and we need you to work on it. This also takes months and months of work. And if you want to be really an expert, it may take years actually to figure out exactly what's going on. And assuming that the training cost of a new developer of a new project is maybe $100,000, euros, you name it, well, then that's actually the budget that you can have, or that you can also put in for training and program-specific expert on your program. Next challenge is test generation. Test generation, although being one of the oldest techniques, still needs advances, notably in order to be sure to see all the possible behavior. This will still need advances in possibly by using AI. There's plenty of work that actually uses AI and LLM these days in order to guide test generation towards those places that are not yet covered well enough. And of course, also by the needs of an AI agent. Namely, an AI agent needs more information about a particular situation. Well, let's guide test generation towards that. The third challenge is going to be entirely non-technical. We're talking about social challenges here. What it will mean to have AI not only just build, but also maintain code, and then coming up possibly with better code than humans will ever have written, possibly writing its own code. We're not just talking about but now even senior developers being challenged by AI. We're talking about risks for the entire society, which we will need to very carefully think about. The good news is that the challenges here will still require a couple of years of research. So we have time to think about the social challenges, and we also have time to weather out the upcoming crash of AI. And then once AI has crashed and we're back into rebuilding things, that's when these techniques would finally come into play. Okay, that's already at the end of it. Should AI coders experiment more? And of course, the answer is a resounding yes, 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 they should. What we have seen is, welcome to the era of experience. Future AI systems should be driven by experience as it comes to coding. Learn from millions of executions of existing code to find out what does this code actually do, to be able to treat and to handle and to maintain and to test and to predict mission critical software that is far beyond the capabilities of any LLM-based coder these days. And I've shown you two first experiments in this direction. First one being able to relate inputs and outputs and learn from that, learn transformer models from that, predicting inputs from desired outputs. And a second line of research where we go and do the same thing for code changes, where we declare, okay, I want a particular change in behavior, and then our system can happily predict what code changes or configuration change might be required for that. With that, I am happy to close, and I think we have some time for questions. Thanks a lot.
Yes, thank you very much. If people have questions, you can raise your hand in the chat, and then or you can raise your hand, and I see a hand already, and oh, the hand disappeared again, so I guess there was an applause hand. But if you have questions, raise your hand, and we'll give you access so you can speak on the microphone, switch on the camera, and ask your question in person. And I get to start. So one thing I was wondering about, so it was very interesting, and it made me think. It also made me think about. So you say we need a lot of era of expertise. It's the era of expertise, and we need to generate all this data. But what now if people start to train the AI models with all kinds of malicious data, and then are we not off far worse than we are right now?
The thing is that you would, of course, train your model on the data as you see fit, and you would train it on data, and you would train it on the data that you consider most relevant for your work. So if you are maintaining an existing system, you would train it with data as you expect it to occur, and of course also a couple of outliers in there, such that your expert can give you answers on the most common data. However, if you are more of if you're more in a testing, if you're more of a testing kind, then you would of course also go and train your model with uncommon data,
Mm-hmm.
which would actually mean that your model would also be able to predict what uncommon data would be required. And this can indeed be misused by people who would be able to then come up and systematically detect weaknesses in your software and have a model that you can ask, what do I need to do to hack into Teams in order to whatever, change the color to blue or whatever. The good news is that while you would be training your program expert, you would discover lots and lots of such errors in the first place, and lots of vulnerabilities in the first place too. And then you can go and ask your own program expert, what vulnerabilities are there in my software, and how do I need to fix them? And the system will fix them, and you can do that well before your software goes out into the wild. So all these techniques are set to actually favor those who defend against those who attack, and therefore, actually, in a grand scheme of things, these techniques will actually make software much more robust and much more predictable, much more reliable than they are today.
Okay, yeah, but they do require that you think about what you're doing in the end, right?
Yes. The other good
Yeah.
news, of course, is that when you think about networked software, for instance, all you need to do here is to limit the access to your software such that if anyone wants to come up with 1 million inputs to your network software, you typically leave them out. While you, of course, who are in control of your software, you can easily run these experiments yourself. And this also gives you a huge advantage.
Thanks. And Andy, you had a question?
Yeah, first of all, thank you for a very inspiring talk. Very nice. So you talked about, let's say, the huge training efforts that these techniques would take, but you also compared it to, let's say, hiring and training people to do it. But clearly, I mean, a human brain, let's say, takes, let's say, 30 watts to do this kind of things.
Yes.
Whereas these LLMs do not, they take a lot more than that. So could you comment on, let's say, the sustainability angle
Yeah.
of all of this? Because that would also be interesting, I think.
So for the modelizer work, which you see here now in the lower left corner, Actually, there we don't train LLMs. We also don't have money to train LLMs, I should say that. But there we train our own models. And the cost for training such a model for a decently sized program, a couple of thousand of lines of code, this is on the order of, we just did the math earlier today. This is on the order of using electricity of 5 to 6 euros, if I recall things correctly. I can even train these models on my own laptop for
And what about
4
inference?
hours.
Because
So that's not
nowadays inference takes much more energy consumption than the training.
that is correct. But the thing is that these models, but the size of these models very much depends on the range of behavior the software has, and also they depend on how easy or difficult it is to approximate the behavior of interest with, in this case, with a transformer model. So I cannot exactly predict how much effort this takes, but what we found so far is that that our transformer models that we extract, the specific transformer models, take, even when executing them, even when asking them, take far fewer resources than the big models that we have, that we need from LLMs.
Okay.
Right now, we are using LLMs only for the purpose of interpreting natural language. That is, we want a ChatGPT-like interface, so we need the ability to interact with natural language. We need the ability to interact with code. That's also best done with an LLM. But both of these are features that need to be trained only once. The training of the individual systems, that's actually something where you don't need to retrain an LLM from scratch for. That's something you should be able to do with much, much smaller models.
Okay, nice. Thank you.
Other questions? People are still thinking. Yeah, I see a question.
I see someone here.
Yeah.
Samin.
Yes. So.
Samin, go ahead.
You need to unmute yourself first, I guess.
Yes.
If you can. I am not able to unmute. Okay, over to you, organizers.
Ooh.
Yeah. Help Sanne.
I gave everyone the option to unmute themselves. I'm not sure.
Otherwise, you type your question in the chat.
Exactly.
Yeah. It should be possible for you to unmute, but that's what Microsoft tells us.
Future program-specific experts will be able to answer that question immediately and tell you which buttons to click.
Yeah.
We're not there yet, obviously.
Yeah.
So, what do you see as the most promising real-world application of this work in the next few years? Well, in the next few years, I see this mostly I'm going to see this still mostly confined to labs, so at least for the next year, maybe for the next 2 years. But after that, this is going to be your programmer buddy that you always dreamt of. So you will be working on code, and you can ask any questions to your buddy, and your virtual AI buddy will know what to do and how to do things. And at some point, you will find out that your AI buddy may even be better at suggesting code that you do, and then you will wonder how long it takes someone else to find that out. But for first and foremost, when I'm thinking about the countless days and nights I've been sitting trying to find bugs and trying to understand how things work, I would love to have such a buddy, if only for the debugging part. Finally, some AI entity that can explain to me what is going on in my program, why are things wrong, what do I need to do differently. Oh, that would be such a great application. And if you think about that, debugging is the one activity in software development that is the least to predict, or the most difficult to predict how long it's going to take because it's an immense search problem. Having something that helps me navigating through all this, this would so boost my productivity. This is something I would really, really love to have. And well, who knows where this is going when our AI will be able to experiment. This is, yep, a very, very challenging, a very, very, for me, a very, very interesting question.
And any other questions? So,
Thank you too.
yeah. So maybe one thing I'm wondering about is also with all these things that are happening, and so, and I work in software verification. So and what should we then? How should we continue if we get bug-free code? Then what's left for us?
I'm happy to report that since these techniques are all based on testing, you will always be able to quote Edgar Dijkstra on this, that this code has only been tested and it has not been verified. So this still continues. And
Yeah.
while this talk was mostly about teaching AI the ability to test, there's also a super interesting line of teaching AI the ability to verify things, to formally verify things. And already right now, I'm talking to colleagues in formal verification, and they're super happy using AI to help them finding the necessary loop invariants, the necessary recursion invariants in order to complete their proofs. There's also an immense potential in here. And in particular, given that today, well, most verification tools, as far as I can see, still require a PhD level expertise in order to figure out how to best use them and how to navigate around their quirks. Having an expert, having an AI expert that tells me or that uses the verification system, that comes up with its own, that learns its own experience and how to best do software verification. Oh, that would be so great. Finally, we would have software verification for the masses, and then the community can continue. The community can have so much fun building the best software verifiers in the world. And then we'd have an AI translating between the common people and the super sophisticated AI and super sophisticated verification systems. I would absolutely love to have these things because I also know I'm always happy if a piece of software is well tested. That's already something. But of course, if I have a proof that it works, that's the ultimate goal. So bring it forward.
Yeah, but it does require that you also know what you want to verify or what you want to test.
Yeah.
So that's I think
Mhm,
that's at some point, if I let my AI decide what I want to know about my code, well,
mhm.
okay, then at some point we get to the butcher that's testing its own meat, right? So
Ah, Testing also requires
yeah,
properties to test, so there's no difference here between
yeah,
verification and testing,
yeah,
except that in testing you may get along with concrete values to test against,
yeah,
but
that helps.
it will also be, but this will also be an important challenge. Say having an AI correctly interpret what you actually want the software to do, inferring this from documentation or inferring this from common sense, whatever. Your software should not crash, your rocket should not burn up, your energy consumption should not go to infinite levels. But beyond such
Yeah,
such generic properties, yeah, of course, someone will have to make the decision what this software is supposed to do and what it should achieve. An AI cannot make that decision. Well, an AI can make the decision if it has a general goal there, but somebody has to specify what the software should be doing.
yeah.
And that's still something that I hope that we, as future designers, architects, and developers, will still stay in control of.
So let's hope that that's so we still have something to work on for a couple more years.
Oh, yeah,
Um,
yeah.
I think I don't know, unless there are other questions. I think it is time to wrap up this uh, for this IPN colloquium. So of course we will continue with the next one end of January, where Anna Paiva will talk. We're waiting for a title so we can start advertising it. For now, I would like to wish everybody very good holidays, and then we'll see you back in 2026. And
Yep.
thanks,
Thank
many
you.
thanks, Andreas.
My
Thank you,
pleasure.
Andreas.
See you soon. Bye-bye.